This program is on basic ball bearing types and the various conditions which caused all of these bearings to fail prematurely. Many authorities estimate that at least 2 out of 3 ball bearings fail before they should. There are many ways to prevent this high percentage of bearings from failing prematurely. The action which wears out a ball bearing is interesting. The balls are harder than the raceways, about 62 Rockwell C as compared to 58 Rockwell C for the races. As load is imposed, the harder ball is mashed into the softer ring, causing the race material to flex. As each ball passes a given point, that area is flexed again and again. Any constant flexing of metal, such as this paperclip, causes metal fatigue with obvious results. Metal fatigue in a bearing causes a condition known as spalling, which looks like this. When a bearing fails from metal fatigue, it has usually lasted an appropriate amount of time. However, this amount of time is greatly affected by the amount of load on that bearing. For example, if a given bearing supported a 1,000-pound load at a given RPM and could be expected to last 1,000 hours, that same bearing supporting 1,200 pounds at the same RPM would be expected to last only 500 hours. And if only an 800-pound load is imposed, the bearing could be expected to run 2,000 hours. A 20% change in load causes a 50% change in life expectancy. Doubling the load on a bearing will cut its anticipated life to 1/8. Therefore, machines which are loaded more heavily than anticipated when they were designed will always have short bearing life. Bearings that fail from metal fatigue after years and years, or after a very short time, probably are lasting as long as possible. There are, however, 2 conditions which will cause a bearing to look like a normal fatigue failure, even though it is a premature failure. Everything that comes into contact with a bearing, particularly the shaft and the housing, has an effect on how long that bearing will last. Here is a bearing that was forced over a shaft much too large for it. The inner ring is cracked all the way through. Much less dramatic, but just as deadly, is a shaft only slightly oversized. As the bearing inner ring stretches, it may take out all the clearance between the components. It is quite possible to impose load on the bearing from the pressure exerted by an oversized shaft. When the balls are pressed into the races, the bearing feels this as load, and load is load no matter where it comes from. This load dramatically affects the bearing and will cause the bearing to look as though it were a normal fatigue failure, even though its life was quite short. Similarly, an out-of-round housing may distort the bearing. Here, the red arrow indicates bearing load. Here again, this extra load greatly affects bearing life. There are many excellent publications which show the correct dimensions for shafts, including the proper fillet radius for a given bearing. Appropriate housing dimensions will also be listed. A particular note needs to be made concerning dimensions. Almost all unmounted ball bearings are manufactured to metric dimensions. However, clearances and tolerances are expressed in inch dimensions. 1/10,000th of an inch is the standard unit of measurement for bearing tolerances. This common paperclip is approximately 40,000ths of an inch in diameter. A fine human hair is 2,000ths of an inch, or 1/20th as wide as the paperclip. The common unit of measurement of 1/10,000th is yet again 1/20th of the width of the hair. Ball bearings are manufactured in various grades of precision. The maximum and minimum shaft size for a grade 1 precision bearing, approximately 1-inch bore, is .9844 to .9847, or 3/10,000ths variation. The bearing bore range is 0.9839 to 0.9843. The recommended interference should average 0.00045, 4 1/2 10,000ths, or less than 1/2,1000th of an inch. A similar bearing this large should be pressed only 6 1/2 10,000ths, still much less than a full 1,000th of an inch. It is common practice to assemble bearings with a specified internal clearance. This is necessary to compensate for the effect of various press fits required for the wide range of applications. When troubleshooting bearings, always check shaft size and geometry as well as the housing. Oversized shafting and out-of-round housings will usually be indicated by premature spalling. Ball bearings come in various series. Often it is necessary to redesign and use heavier bearings to solve frequent failures due to spalling. By far the biggest contributors to premature failures are contamination and lubrication failure. Bearing races have a very bright mirror finish. This finish remains even when the bearing is spalling. The destruction of this surface finish will destroy the bearing. Any material which destroys this finish is called a contaminant. Marks such as this on the finish are certain signs of contamination. A foreign material of some description found its way into this bearing. An illustration of how cuts and tears weaken a material may be made with this package. This material is quite strong until a tear is started. Then the strength is virtually destroyed. Similarly, when contaminants from any source, such as this dirty workbench, get into the bearing and scratches or marks the raceway surface, the material strength is greatly reduced. Contaminants come in many forms. These include rust, which may form if improper lubricating procedures or the wrong lubricants are used. It is important to pay particular attention to rust inhibitors in lubricants for applications that involve seasonal operation or equipment in wet and humid conditions. Dirty hands and workbenches, along with contaminated lubricants, are by far the biggest bearing enemies. Contamination occurs most often during the installation process. Any bearings, whether common and inexpensive, or an industrial jewel worth thousands of dollars, may be destroyed by the smallest particle if that particle gets to make its mark on the bearing raceway. Here you see a spalled spot. It's quite obvious something got into this bearing. A ball rolled over that something, and the bearing failed prematurely. It's not necessary to wash new bearings unless they get contaminated. When washing a bearing, always use safety solvent. Never spin a bearing with an air gun. They are not intended to run at high speed unless they are contained in a housing. They may literally explode and cause great personal harm. Filtered air may be blown through the bearing to dry it, but the bearing must be held so that it does not spin. In addition to the personal danger of spinning a bearing without an oil film on the components should never be rotated vigorously. This will damage the finishes. Physical indentations such as this are known as Brunel's. Notice that the marks in the raceway are the same exact spacing as the balls in the retainer. This was probably caused by the improper use of a press. Note here that the pressure from this press is being applied directly on the rotating parts. The harder balls have the capacity to make permanent indentations in the raceways. Therefore, it is important to properly support the piece being pressed. In this diagram, tremendous force may be exerted with no damage to the rotating elements. Brunel's may also result from the improper use of a hammer and may occur from a relatively light blow. A Brinell bearing is normally quite noisy and will fail in a short time. Bearings such as this are normally pressed on the shaft or heated, slipped over the shaft, allowed to cool, and shrink into place. A clean, controlled heat needs to be applied until the bearing reaches 250 degrees Fahrenheit. If the bearing is not heated long enough, it may cool and seize on the shaft before it's positioned properly. A condition known as false Brinelling is caused by vibration and jiggling of a bearing that is not rotating. The false Brinells may be made across the bearing raceway or run in the same direction as a normal ball path. Vibrating action wears away the oil film, and continuing action causes the finish of the components to be marred. False Brinelling of this type may be prevented by occasionally turning on standby equipment or even rotating it by hand. This redistributes the lubricant and also changes the vibration points. Proper supportive equipment being transported also helps prevent Brinelling and false Brinelling. Bearings accommodate two kinds of load, radial and thrust. Thrust load is an axial load which is imposed on a bearing from either direction. Radial load is imposed on a bearing in any direction, like this. Recognition of thrust failures requires the ability to recognize bearing types. Here are three bearings, all exactly the same size. This one, the most common, is known as a Conrad type. This bearing has notches cut into the raceways that allow the addition of more balls. As the two bearings are compared, it can be seen that the one with the notches does indeed have more balls. It is referred to as the maximum capacity type. Another variation is this, where one complete shoulder of the bearing has been machined away. Notice how much wider this shoulder, known as the back, is than the other side of the ring, known as the face. This is referred to as an angular contact bearing. Angular contact bearings are intended to accommodate thrust load. However, it must be understood that they have thrust capacity in only one direction. This angular contact bearing was positioned with the load applied from the wrong direction. Loading notch thrust failure occurs when too much thrust is applied to the max type bearing from either direction. Most bearing applications require the bearing to accommodate a combination of thrust and radial loads. The Conrad bearing is most suitable for combination loads. If load is mostly radial, a max type may serve best, and of course the angular contact is designed to accept one-way thrust. Angular contact bearings are often used in pairs. When these are mounted in a face-to-face or back-to-back arrangement, they can accommodate thrust in either direction. They may be mounted facing the same direction. Therefore, it is extremely important to replace angular contact bearings facing in the same direction as the original installation. Another ball bearing, which has very little thrust capacity, is this, the double-row self-aligning ball bearing. Most ball bearings are not designed to accept misalignment, and a misaligned bearing has a short life. As usual, the components of a failed bearing generally indicate the cause of the failure. Here, the ball path moves from side to side in the stationary ring, and a strange pattern appears in the rotating one. Also, the retainer is broken, which is another strong indicator of misalignment. Causes and cures for misalignment are obvious. Proper alignment of equipment is very important to bearing life. Another fairly common failure is caused by electric arcing. Pitting of the raceways from electricity is called fluting. Never allow an electric current to pass through a bearing. The next type of failure is from lubrication. This falls into two categories: the improper kind of lubricant or the incorrect amount of lubricant. Grease takes on the characteristics of the oil it contains. The most important consideration is the viscosity of the oil used. The NLGI number, such as number 2, only tells the user the consistency of the soap or fillers used in a grease, but nothing of the lubricating characteristics. Follow the recommendations of the bearing manufacturer for the proper grease selection. A totally filled bearing cannot operate properly. Some grease must be displaced immediately when the bearing starts to rotate. If the bearing operates completely full of grease, it must churn that grease, which can cause a rapid temperature rise. The topside limiting temperature for many popular lubricants is easily exceeded by heat caused from this churning action. When the surface of the balls and retainer hit this critical temperature, the grease carburizes. The lubricant then becomes ineffective, and the bearing fails from a lack of lubricant. Bearings should be filled approximately 1/3 full. Overfilling is a very common problem. Undersized shafting can cause problems with the inner rings of pillow blocks. This three-corner breakout is evidence of an undersized shaft. Again, this illustrates that everything which comes into contact with a bearing, such as the shaft, the housing, lubricant, and even your hands, have an effect on how long that bearing will last. Make certain the correct bearing type is used as a replacement. Observe the parts of the failed bearing and look for signs of premature failures. Last but not least is this failure. It is an STUPID, stupid failure. This bearing was left unwrapped and unprotected. It is a very expensive bearing, and it is no longer serviceable. It has failed even though it was never installed in anything. In summary, to prevent these premature failures, remember to keep bearings wrapped and protected until installation time. Keep work areas clean and free from contaminants. Check shaft size and housing size for proper dimensions per the manufacturer's recommendation. Follow proper press fitting and shrink fitting procedures. Use a clean lubricant of the proper type and amount. Be sure the same bearing type is used for replacement. Pay close attention to the direction that the bearings face when mounting angular contact bearings. Rotate the shafts of idle equipment periodically. Never allow an electric current to pass through a bearing. These steps will help ensure that you get the expected life that the manufacturer has built into the bearings.